Welcome. My name is Ian Mazza. Today we're talking about how to create the optimal power delivery network for applications in robotics. If you're responsible for designing power systems for robots, you've probably got multiple requirements. You want to maximize runtime and range. You want to increase and add payloads. You want to improve safety and reliability. You want to add new functionality, and you might even want to change existing functionality. But for all these things, you want to get them done fast. So we're going to go through some real-world examples in robotics to show how you can use a modular design approach to design a system that can be optimized for any or all of these requirements. In this webinar, we'll go over two real-world examples based on the work we've done with leading innovative robot manufacturers. We're going to focus on two specific applications, tethered robots and delivery robots. But the information here is useful across all robotic power systems. By using specific applications, we will show how creating a power delivery network, or a PDN for short, at the beginning of the design process rather than at the end, and by using high-density power modules instead of discrete components or centralized power supplies, gives an optimal solution to meet your system's requirements. We found that when you wait to design the power solution at the end of the design process, you risk creating a custom PDN that is difficult to reuse as a platform, or expand its capabilities quickly and easily. With some planning, swapping out a sensor or upgrading the payload capability won't force you to redesign the entire power architecture. Before we dive into the examples, I'd like to explain the concept of the power delivery network. So a power delivery network, or PDN for short, is more than just the power supply. It describes both the source of energy and all the loads, which in the case of robotics is a collection of motors, sensors, high-power processors, and other electrical subsystems, but also the strategy and implementation of how the power is distributed throughout the system. Take, for example, mobile robot batteries, which are an energy source ranging from nominally 12 volts all the way up to 400 or higher, typically routed to directly power the propulsion motor drives. But there are other voltages needed within the robot that are different. These motors may operate at 12, 24, 48, or even 70 volts or higher. Sensors can be at 5, 15, or 24 volts. And the processors can run at voltages that are 1 volt or lower, and you can even have a GPU card in there running off of 12 or 48. Now, some PDNs are as simple as a single central power supply that puts out all these voltages, which are then routed to each subsystem in the robot. It's also easy to implement, but it's not flexible, and we typically call it a silver box solution. While the selection of the box may be efficient for your time, having to route all those different low voltages can consume space and weight of the box and the cables, which also makes it susceptible to noise and external interference. Another option is to build the entire power supply yourself using discrete power components, but that requires considerable expertise, time, and effort. Now, if you have those, that's great, but if you need to change something at the end of the design process, it can be disruptive and risky to your schedule and the technical requirements. So the silver box is easy to design, but doesn't give you much modularity to change or expand. The discrete solution is hard to design, and while changes are possible, it will take time to repeat the work and revalidate your designs. Fortunately, you can get these benefits without the drawbacks by using a PDN that uses modular power components to convert the energy source, which is done more easily than the discrete method, and these same modules can be swapped or scaled to meet the growing demands of increased power per load or additional loads. This modular approach, when adopted at the start of a design, will create a platform for a power architecture that can be more easily expanded than a silver box, while also providing high-efficiency distribution in lightweight modular packages that allow for easier change compared to a discrete design. Put simply, if you change the outputs, you don't have to redesign the entire supply or repurchase a new one. Instead, you can simply add the new module for the additional capability. Now that you understand the value of a modular approach, I'd like to turn this over to one of our technical expert application engineers.
I'm Tom Curatolo, Senior Field Applications Engineer. Now that you understand the value of a modular approach, I'd like to apply this methodology to our first example, tethered robots. Tethered robots, also referred to as ROVs, remotely operated vehicles, are often used when a mission is needed close to the host vehicle or control base, and for long operating times, such as in hard-to-reach or dangerous underwater environments, eye-in-the-sky surveillance, construction inspections, or over line-of-sight communications. In order to control the ROV, a tether cable is used to provide power for extremely long run times and for secure and reliable data transfer. The cable is also a safety mechanism for an underwater robot in the event of a fault that requires recovery of this valuable asset. Here's our first example of an underwater robot using a tether. In this application, one of the biggest challenges is designing a lightweight tether that doesn't add to the robot's weight and/or drag, while also being able to deliver power efficiently. These two requirements are typically at odds with one another, as propulsion and electronic payloads work typically from voltages ranging from sub 1 volt to over 50 volts, making any length of tether very lossy. This leads the designer to consider higher voltages up to 1,000 volts as a source and address the tether as a high voltage transmission line that then transforms and regulates back to the needed voltages on the vehicle. The figure shows the basic trade-offs that are involved with this decision. Assuming the goal is for the ROV to expand operating range with minimal impact on vehicle design, you can see the voltage drop and losses of a 16-gauge cable with a 9.9 millimeter diameter versus a 20-gauge cable with a 6.4 millimeter diameter that were used as buoyancy-neutral tethers at various lengths for a 3-kilowatt vehicle with either a 400-volt or 800-volt host supply. By dramatically increasing the tether voltage, we can significantly reduce the diameter and weight of the longer cable, creating less drag on the robot's maneuverability, and reduce the overall losses that the tether incurs, plus the inherent instabilities caused from excessive voltage drops on longer tethers. In the underwater ROV system, the use of a fixed ratio converter, shown as the BCM, bus converter module, will transform the arriving voltage down to the appropriate bus voltage, and then followed by the appropriate regulators to provide each specific load that required regulated voltage. Another example that was provided by Vicor FAE Stavros Dokopoulos, who has extensive experience with tethered robotic designs, is a situation where a customer wanted to power more payloads: sensors, computers, LEDs, etc. The host supply provided 750 volts DC plus or minus 5% to a 1,000-foot tether to handle 4,000 watts of peak power, plus some payloads and accessories, such as 2,500 to 3,000 watts for thrusters needing approximately 40 to 50 volts, 100 watts of LEDs with 2 amps at constant current, control computing module with 12 volts plus or minus 5% at 150 watts, cameras and sensors with 15 volts, 100 watts each with an isolated return. A cursory calculation shows a tether with reasonable ampacity above 7 amps will have less than a 30-volt drop at full power. So the first key component is the high-voltage fixed ratio converter, boasting greater than 97% efficiency, utilizing a transformer-based series resonant topology without regulation, making for a clean, low EMI, and highly efficient conversion. Loads with the same ground can be powered by a non-isolated buck or buck-boost converter without the need for isolation. The camera and sensors need a separate return, isolated from others, so using a small, lightweight DCM, DC-to-DC converter module was acceptable. A thin bus wire was run across the vehicle to the loads, and each has its own converter. By considering the power delivery network at the beginning of this design, the customer was able to optimize the design of the tether, improve overall robot performance, reduce cost, and improve the intended modularity. Another option to consider is if the host supply has the capability to compensate for the voltage drop. That is, to increase the tether voltage as load increases so as to always have 800 volts at the vehicle. In this scenario, the host supply can dynamically raise its output up to 900 or even 1,000 volts, and as a result needs to supply an additional 400 watts to compensate for losses. Since this approach compensates for voltage drop on the tether up front, the voltage regulation part of the high voltage DC to DC converter can be removed, reducing related losses in space. Another comparison to consider is that an array of 6 500-watt compact DC to DC converters powered from a 400-volt tether and regulating the vehicle voltage to 48 volts, irrespective of tether voltage drop, including heat sinking and input filtering, would weigh less than 1 kilogram and take up a 12 by 17 centimeter board space with a height under 3 centimeters. For a high-density solution with a compensated tether voltage, you can use these fixed ratio DC to DC converters. BCMs are less than half the size and half the losses compared to regulated converters. Two 1,650 watt fixed ratio bus converters are the same size and weight for either 400 volts and 800 volt inputs, and also have built-in telemetry using PM bus. In regards to future design improvements, increasing tether length for greater depth may increase drag even if it is thinner, and thus may need more power to compensate. Fortunately, with a modular power delivery network, it's easy to add additional power or capability as needed. Let's take a look at another example. Delivery robots. Unlike tethered robots, delivery robots need to be able to roam free, often in complex, busy terrain, such as city sidewalks, streets, paths, and stairs. They need lots of GPU power, logic, sensors, and long-range capability to be able to make it to multiple destinations and still have enough energy to return to a charging station. In regards to the PDN, efficiency, meaning less losses in heat dissipation, weight, small size, and scalable power is important. These robots also need to carry as many packages as possible, and because these packages need to be secured within the robot, space is at a premium. The less space a power solution takes up, the more space available to carry packages. Here's an example using a 24-volt battery and a 750-watt power delivery network. The 24-volt battery needs to support not only the motors that propel the robot, cameras and sensors to guide and protect the robot, a computer and GPU to process sensor signals, vision for control of the robot, wireless communications, lights, and other peripherals, such as the locking mechanisms to protect the packages, doors, plus heating or cooling requirements of the payload. If your robot needed more runtime between charges, the PDN needs to adapt. Upgrading from a 24-volt battery to a 48-volt battery will increase the power density of the energy storage and extend your runtime. This presents two challenges to your robotic platform and the power delivery network that supports it. First is, how do you adapt your PDN to a 48-volt supply and distribution in the same space without additional weight? Second is, how do you do this as quickly as possible? Fortunately, DCMs come in a variety of input voltage ranges, such that 24-volt parts can be swapped with 48-volt input parts of the same size and power capability. In this case, it becomes a straightforward replacement to the original layout with minimal impact to the overall design used with the 24-volt battery system. Once again, designing your power delivery network up front and using a modular approach not only helps achieve greater performance, but it also allows for quick and flexible scaling for future changes.
While these are only two examples, they are extensible to other robotic designs. In fact, this modular methodology is useful across industrial, computing, and automotive applications too. Whatever the application, remember that you can create the optimal power solution for your system by first using a power delivery network to create, distribute, and deliver power to your loads. You'll save time and have an architecture that can be expanded or scaled as needed. Second, selecting small, lightweight, modular components. They give greater flexibility now and the capability to reuse and/or expand in the future. Thanks for joining us today.
Ian and Tom, our first question is this. In regards to the 24-volt delivery robot application, what if there is no requirement for isolation? Are there any trade-offs to consider?
Good question. In regards to the 24-volt delivery robot application, it was shown with the Vicor DCMs, which are isolated DC to DC converters. But since it's a lower voltage and safety issues aren't as critical, oftentimes this type of an application may not require the isolation that you get with these type of DC to DC converters. In that case, the opportunity is that smaller parts could be used, like buck boost or buck regulators, that take up a lot less space and can probably save some cost as well, and there's certain advantages in that regard. However, if isolation is required, I mean, that's how we presented it, and even at the 48 volt, we presented it with isolated converters.
Just maybe to add to what Tom said, if you have a 48 volt input, we have a non-isolated fixed ratio converter called an NBM. So it's fixed ratio, non-isolated again, and that converts 48 to 12 ratiometrically at a very high efficiency. I think it's 98% or higher in a package that's surface mount, only 23 by 17 millimeters in area. I think it's 7.5. But we might actually have a version that's coming out that's smaller or lower profile than that. So if you want a ratiometric conversion, an unregulated solution, there's also that as an option.
What is the highest input voltage of the BCM?
So of the units that we offer today, the one that Ian had mentioned, the BCM 6135, that has an input range of 520 to 920 volts. So we go up to 920 volts presently, but Ian, I think you have some updates for us in that regard?
Sure. Also on the website, we talk about some future products and some capabilities. In that same size and the power level that I talked about before, that's 6135, kind of 80 amp capable, we have the ability to increase that input voltage range all the way up to 1200 volts for the same kind of BCM capability. So the K factor would probably be a little bit higher, maybe 1/24 to get down to a cell level. I personally have, I guess, been in meetings and heard customers even ask about 1500 volts, but that's been primarily with solar panel arrays and not so far with drones. But I'd be just curious if that was coming about or if people saw a path to higher voltage or not.
Okay, next question. I have high power requirements. Can I parallel your fixed ratio converters?
Yeah, so that's a great question. Certainly scaling the application is something that probably some folks are very interested in because they probably have a lot of different robots that they may be working with. So the ability to easily scale the power supply once you've completed it is a big advantage. So the fixed ratio converters, the BCMs, are easily, and I want to stress that, easily parallelable. It's like paralleling FETs. So there's no significant control lines or anything. It's pretty straightforward. So that makes it very easy to do, as well as with the DCMs too. If we can just extend to that product line, the paralleling scheme is it's a droop load sharing scheme that makes it very easy to parallel these and provides, if you will, in some cases, fault tolerance.
And to just add to Tom's point, I mean, when you parallel them, you have to just make sure that they're seeing the same impedance, each one of them, and that's how essentially you get them to work well in an array. But to Tom's point, it requires very little additional components to make an array, no matter how big it needs to be.
What is the size and weight of Vicor's fixed ratio converter?
I'll take that. That's an interesting question. What's interesting is Vicor, for the fixed ratio converters, refers to them as BCMs. And we also, in the part number, put the dimensions of, as an example, a BCM 6123, which refers to a 61 millimeter length and a 23 millimeter width. And that part is under 7 millimeters in thickness. And the weight is roughly 61 grams. So that's one of the larger sizes that we have. Also, we've got smaller BCMs that are about 1 inch square, and those are a bit lighter too. So there's a variety of BCMs that can be easily accessed for these type of applications.
And maybe just to add to that quickly, there's some new BCMs that are on our website and going on the website as new models come out that are in that 61 millimeter by 35 millimeter size through-hole pins. They're around, I think, a little heavier than what Tom said. They're 70 grams about, but they're up to 80 amps of output current. So check them out.
Would you explain again why you can remove one output channel by raising the input voltage from 800 volts in to 900 volts in of Tether?
Okay, so this goes back to the Tether application where we were comparing it to a source providing 800 volts. Now, if the source just provides 800 volts, of course you're going to have a drop in voltage as it runs through a very long tether. And therefore, when it reaches the robot, it's not regulated, and hence the regulation has to occur, on board the robot with the DC to DC conversion, and that's where we get into the fixed ratio converters, followed by DC to DC converters that provide regulation. However, we also talked about a compensated application where the source is providing 800 volts, but compensates for the drop in the tether such that it provides 800 volts at the robot when it reaches the robot. So therefore, the source is changing its voltage as high as perhaps 1,000 volts to compensate for that voltage drop through the tether. So what we were getting at the point there is if you're doing this compensation with the source, you've got a regulated voltage arriving at the robot. And in the instance of the thrusters, I think in that specific application, the regulated voltage is sufficient for those so that you don't need to add a DC to DC converter. Hence, we're showing that for that one specific load, you could remove the DC to DC converter that's on board the robot, and then save in regards to efficiency and additional power losses. So that could be another advantage in this type of an application.
Are fixed ratio converters semi-regulated?
That's a good question. In the examples that we were showing where we were using the BCM, this is a sine amplitude converter. And basically it's if you will, conceptually, it's a DC to DC transformer. So fixed ratio means it's not regulated, it's not semi-regulated. It's just basically a turns ratio or a K factor, as Vicor calls it, that delivers a voltage related to the input voltage. So this is why we refer to it as fixed ratio converter.